Hello everyone. So in this session I will be explaining the design of canal drop. First of all, you should know what I mean by the canal drop. Canal drop is the one which is structural irrigation structure which is provided whenever there is a sudden change in the bed slope of the alignment of the canal. So where is the ground, if it is very steeper, suddenly if the ground profile changes, and we can't provide the canal like that, because if we provide canal along that line only, there will be the erosion of material which is taking place due to higher slopes, and flow will be at a higher speed, and therefore erosion of the material will takes place. So in order to avoid that, the water will be allowed to fall, and then so it will become stagnant, and then it will be gravity flow will be taking place. Okay, and such structures has to be designed. So there are actually several types of canal drops which are there, and they depend upon the topography of the canal, and as well as economy of excavation or filling can be achieved. Okay, so depending upon the topography, etc., we will explain that different type of canals which are the canal drops which are there. So Oogie Falls, Rapid Falls, Stepford Falls, Trapezoidal Notch Fall, Well type of fall, simple vertical drop fall, straight glacis fall, Montague Canal fall, and English falls or Baffle falls. So the Oogie falls, these first three are the old type of canal falls which were there. So Oogie type of canal fall can be adopted when the water is to the topography is very sudden. If the slope changes suddenly, and so then we can provide a Oogie type of the surface by using rubble masonry, and thereby the flow will be dissipated. The energy in the flow due to fall will be dissipated in the water here. Okay, and these are all the old type of canal falls which were using rubble masonry, and this will be uneconomical now. The next is rapid canal falls. If the slope is not much, okay, there will be long sloping glacis which will be provided by using this rubble masonry, and this require higher material, and this also proves to be uneconomical in these days. And the other type of falls are stepped falls. Here the water will be allowed to fall in several steps, and here also rubble masonry and the brick walls can be used. And so as I said, these three are old. Nowadays they are outdated, and nowadays very usual and simple and popular kind of notch which is provided is trapezoidal notch type of canal fall. And here this is you will have a notch wall, and number of notches will be provided where water will be flowed along through these notches, and we require to design the depth and width of the notch here. Okay, this is the notch wall, and you will have upper upstream side top bank level, and downstream side top bank level. Okay, and similarly other type of canal falls are well type of canal fall. In this one you will have upstream well as well as downstream well, and water will be allowed to flow into this well, so that the energy will be dissipated, and then here it will be flowed like this, and it will be raised up. Here the energy dissipation will take place. Okay, because of the raising up, and the water will become stagnant, and can be gravity flow can be taken place. And the next type of fall is simple vertical drop of canal fall. In this one, uh, there will be a single vertical drop which will allow the upstream water to fall with a sudden impact on the downstream side. So the downstream acts like a cushion for the upstream side water and dissipate extra energy. This type of fall is tried in Sarda Canal. Thereby it is named after Sarda Canal. So Sarda drop. Okay, and the next type of canal drop is straight glacier type of canal fall. In this one, the crest will be raised little up, and the water will be allowed on the straight edge. Here in this is Montague. The picture I am showing is the Montague whereas for the straight glacier fall, the difference is here it will be straight. In Montauk type of canal fall, crest will be raised and water will be allowed to flow on this curved in Montagu, whereas in straight this will be straight, and so water will be allowed on to this sloping ground, and energy which will be get dissipated like this. Okay, so that the abrasion will not takes place. So in this in our project we will be designing a very popular type of trapezoidal the canal drop, which is nothing but trapezoidal notch canal fall, and because of the simplicity, and here we need to design the width, the canal, that is trapezoid notch. We need to design the number of notches as well as the bottom width of the notch and top width and depth of the notch we should design. So in order to design this, we need the bed level, upstream bed level, upstream full supply level, and upstream top bank level, as well as similarly we need a downstream bed level, downstream full supply level, downstream top bank level, and these you have to get it from your longitudinal section final element. So as we know, this will be the formation level of the canal, and from there if you have a if you just give a freeboard of 0.5, you will get the the full supply level, and again offset you can give by 0.75. That one will be the the upstream bed level. Okay, and here as you can see, the total depth will be 1.25. so this is the top bund level, top bank level. That's nothing but the proposed formation level. Below that we will be giving the total depth of the canal equal to 1.25. Therefore, so 921.065 is the top bank level. So here what you should do is, you should consider where exactly this point should be the one where exactly the slope is suddenly changing. So that point we will be providing the canal drop, and here in this case it is happening at 210 meter chainage, and the RL is 921.065. Existing formation, this level is 921.065 will be the RL, and the existing ground level will be differing afterwards. You have to do existing ground level in the final element. Actually these things have to be updated. These are the earlier one only. So this ground level is 921.065. so this is the ground level, 921.065. from there 0.5 for the full supply level, minus again 0.75 you can give for bed level. Okay, so these are the levels you can get it, and similarly the downstream side depends upon where exactly the slope has become steady then. Okay, so here we are assuming one drop, and then we are making the canal drop canal to be having a bed slope equal to 1 in 2000. Okay, only drop will be there in this portion, and remaining portion you will have a normal slope 1 in 2000. Okay, so and in order to get the downstream top bank level, FSL, and bed level, so you should select that point where slope is becoming gradual. So that's actually 917.545 is the RL of this ground level. That's called top bank level. That's nothing but the existing ground level there. Okay, or the one which we are constructing the top. Okay, top of the canal, and bottom of the canal will be minus 1.25. You will get this one, 917.545 minus 1.25 will get this level, bed level, downstream bed level, and downstream full supply will be nothing but 916.295 plus 0.75 or 917.545 minus 0.5. Okay, and in your longitudinal section you should draw these or offset these according to the scale. Actually vertical scale you have taken 1:50, so you should double all these things. Instead of 1.25, 2.5 offset you have to give it. Okay, everywhere, or instead of 0.5 it should be 1, like that you should give it. and these are the levels. So making use of these levels will let us design the canal drop. So for the design of notch type of canal drop involves these values. So in your report you have to change these readings, okay. 921.0, yeah, you just update all these things and assume, and the ground level, existing ground level will be here, okay. Existing ground level, because this is the final element. After final element, this is the existing ground level, and that's equal to 917.95. And assuming good foundation level at 970, then let us take up the design. So in order to design the notch, that is number of notches, and as we have seen here, number of notches we should fix, and the dimensions of the notch. So here let us, because it's a very small flow, we'll assume one notch only, and also the amount of discharge which is coming out of the sluice is 0.63 meter cube per second. So in order to find the dimensions of the canal drop, canal notch, trapezoidal notch, so we need to assume two discharges. One is full discharge, full supply discharge, and half supply discharge. By imposing those two conditions in the equation of trapezoidal flow, so trapezoidal notch flow, we could be able to get the bottom width, that is L, as well as the slope. So we need to find the slope and bottom width, thereby we can get the top width. So in order to get these things, we have to have the formula for the flow in the discharge in the case of trapezoidal notch, and in that we will be considering two cases. One is full supply discharge and half supply discharge. So if we consider full supply discharge, 0.63 meter cube per second is the discharge, and half supply will be half of it. So full supply depth will be 0.75 meter, because we have already assumed 0.75 meter will be the depth. And next, half supply depth will be nothing but, because it's a trapezoid, the half supply depth will become 2/3 of the 0.75. If it is a rectangle, it will be exactly half, 0.75 by 2. But here it is a trapezoid, and area available will be less, so you have to have more depth of flow in the half supply discharge. So it will be usually 2/3 of 0.75, which is equal to 0.5 meter. So now what you can do is, you can substitute this Q as well as this D in this equation, okay, and thereby you will be getting two equations, okay, that is L plus 0.3 n and L plus 0.2 n, and over here other parameters are nothing but Q is the discharge, CD is the coefficient of discharge, and D gravity constant, and L is the bottom width, and H is nothing but height of the flow, okay, and N is the slope. So substituting all these things, if you, for full supply you will get one equation, okay, and similarly for the half supply you will get another equation. So solving these two, you will be getting the bottom width of the notch and the slope of the notch. So bottom width of the notch is 0.35 and slope of the notch is 0.4. So by considering these things, you can find the top width of the notch, which is nothing but L plus ND. Actually this is, yeah, half supply, so L plus of ND only, right? Okay, so this is actually 2 times 1 ND, both it will be ND. So 2 points plus of ND, you will get full supply discharge, and that is top width, you will get it, okay. And actually speaking, this ND is nothing but for the both the depths, okay, for both the widths. So this is nothing but a triangle. So in the triangle you will be able to get this N, okay, and so that you will be getting the bottom slope, right? And the next one is notch type of that is notch wall or notch pier you need to design. So that is nothing but this one. So this notch wall, you can keep exactly half of the width of the depth of the flow as the width of the wall. So d by 2, it will be 0.375, approximately make it to 0.4. The sides of the notch wall are kept vertical, so these are the vertical walls. And then the drop wall and water cushion. So we should fix the dimensions of the drop wall. So we know the the top of the drop wall will be kept at upstream bed level, which is nothing but 919.81 here, 919.81 here. So this is the bed level 919.815. So therefore, and also the top width can be kept equal to 15 to 30 meters higher than the width of the notch wall, so which may come around 0.75. So you can make it equal to 0.75. Okay, so the top width is 0.75. In the depth of the wall, okay, so the depth of wall depends upon the ground level as well as the water cushion. And assuming water cushion is nothing but when the water is falling, you need to have some minimum amount of water, so that which when the water is falling in the water, this water gets dissipated, the energy gets dissipated. And the depth of water cushion can be kept, assume it is equal to 0.25. Therefore the total depth of the wall will be equal to the difference in the bed levels of upstream and downstream, which is nothing but 919.815 minus 916.295, which is equal to 3.52 plus 0.25, which is equal to 3.77, and make it 3.75. So therefore provide 3.75 depth of cushion, drop wall. Okay, and you can keep bottom width of the drop wall equal to 2 meter here. Okay, and then assume the length of water cushion equal to 5 meter, right? And then we need to design, when the water is flowing like this, we need to have a material that is apron, which avoids the erosion. So that apron length can be assumed equal to 2 meter horizontal length and 2 meter inclined length and 5 meter horizontal length. Okay, and so that completes actually the design of canal drop. So we need to show this canal drop in the longitudinal section. So all these dimensions are fixed. So the design summary is 0.4 is the width of the drop wall, 0.75 is the width of the this is notch wall, 0.4 is the width of the notch wall, 0.75 is the width of the drop wall, and 0.2 meter is the bottom width of the drop wall. And below that you can provide concrete bed of 1 meter thickness, and this is rubble masonry 1 meter thickness, and this is the downstream bed level and upstream bed level. Same thing we should you should draw in the longitudinal section. So here what you do, at the point you just from the bed level you draw 0.75 at the bed level. 0.75 is the top width, bottom width 2 meter you can provide, and so this height is 3.75. do an offset, create this structure, and this side you can provide 1 meter extra, and then 2 meter, 5 meter, and so in order to draw this line, what you should do is you extend this the downstream bed level till here, and then join these two lines. Okay, that is, you do an offset of from here, do an offset of 2 meter, offset 2 meter from here to here. Okay, extend the bed level till this 2 meter, and then join from here to here. Okay, join this and then do offset, so that this you will get it, and then from there 5 meter is the apron length you can provide. And after doing this, what you can do is you can remove these lines. You can remove these lines, okay, and extend this water flow level till here. Okay, you can extend this till here, EX double enter, you can do it. Okay, so that's the depth of flow which is taking place. So you can delete only these. So this is how water will flow when from here water will fall, and then water will flow by with the depth of 0.75. Okay, so this completes actually your canal drop design and drawing. And same thing you have to update in the cross section. Okay, so here actually you might have provided placed the canal here in the cross section at 240 meter. So that only cross section has to be updated. And here also you have to draw appropriately, that is you should show the notch and the drop wall and the notch wall. Okay, so that completes your canal drop. Thank you very much.